Okay, in this presentation what we're going to do is look at, this is the key part here. This is show that the expected value of the population variance, the sample variance is equal to sigma squared, which is the population variance. So it's like looking at the relationship between population parameters and sample statistics. So it's just we're looking at variance in this particular instance. Anyway, we have a sample here, x1, x2, all the way up to xn, and it's a random sample of size n from a population with mean mu and variance sigma squared. Let the sample mean be x bar squared and the sample variance be s squared equals 1 over n minus 1 times this expression here, which is the sum of xi squared, which is all the terms here, just square them up, minus n times x bar squared, which is the sum of the square. Okay, you may assume that the expected value of x bar equals mu and the variance of x bar equals sigma squared over n. Now you would just sort of take this here as an article of faith or something that you're given, and we don't have to sort of demonstrate anything related to that, not in this video, but what we do have to demonstrate is this part here. Now the key thing we're going to work on here is base ourselves on that formula there. Okay, so here we go. The expected value of s squared, which is the expected value of the sample variance, that is equal to what we're going to do here is just factor out that fraction 1 over n minus 1. So that fraction, I'll just call it the fraction from now on. We're just going to factor that out. So it's the expected value of the sum of xi squared minus n times x bar squared. Now essentially what we're going to do here is just essentially insert where we have insert the sum, the expectation in here. So essentially what we're going to do here is just like re-express this as the sum of the expected values of x bar squared. Okay, so this expression here, this part of the expression here becomes this down here. Okay, and this part of the expression here becomes this part here. Okay, so essentially we just sort of move the expectation into the expression. Okay, so we have the sum of the expected values of xi squared minus n times the expected values of x bar squared. Oh, x bar squared. Okay, so yeah, now this is where things get a little bit complicated. Okay, so what we have here is we have two expressions here, and I'm going to sort of look at this one in particular. We're going to look at what the inside this summation there. We're going to look at that part there, and also this part here, this expectation here. Okay, now you notice actually they actually do have the same sort of format. The expected value of x squared, xi squared, or x bar squared. Okay, so what we're going to do here is sort of re-express them in terms of the variance and the expected value to be squared. So I'll just color them in there. So the expected value of xi squared, okay, so the squared term, then get the expectation of it. That can be written as follows, okay? Re-expressed as follows. The variance of xi plus the expected value of xi to be squared. Okay, just be careful about the difference, where the squaring term goes. See, it's inside the bracket there, it's outside the bracket there. They are two different terms. Okay, likewise over here, we could disregard that n for the moment. We're sort of doing the same thing over here. This actually was sort of x bar squared, the variance of x bar plus the expected value of x bar to be squared. Okay, you might notice that is actually the same sort of expression here, but this is the actual underlying value, and this is a sort of sampling distribution of the mean. Okay, or related to the sampling distribution, or you just look at it in that sort of breakdown there. This is the underlying distribution and the sampling distribution, or that sort of dichotomy there. But ultimately we're doing the same thing. Just to be clear, if you're not sure what I'm doing, we're using this sort of standard formula here and just rearranging it. Okay, you should be familiar with this. If you're not, you're going too far with this, and you probably should double back to random variables and then come back at this later on. Okay, that's a sort of well-known formula for random variables. Essentially what we're doing is just rearranging that here. Okay, now The variance of xi, that's sigma squared, okay, and the expected value of xi to be squared is mu squared. And then we have the summation of that, okay. Over here we have the variance of x bar, okay, and we were told earlier on that that is x squared over n, and the expected value of x bar to be squared, which is sigma to be squared, sigma squared. Okay, so far so good. Okay, now we got to look. The things are actually starting to simplify quite a lot. This n here, okay, that can cancel out with that. We have the m, but we don't cancel out there, so we have n mu squared. So we have this turns into this expression here. This entire expression with the n becomes minus sigma squared minus n times mu squared. Remember, it's only cancelling out for this n. We just have to transfer the n in here, if you get me. So just multiply it out by n. Okay? Now, sigma, the sum of x squared plus mu squared. Essentially, just it's constant for each value of xi. Okay? So essentially, if there's 10 of them, essentially we just add up all 10. So this becomes n times sigma squared plus mu squared. Okay? So just because it's a sample size of 10 and these are constants. Okay, so we're just adding the sum of two constants up n times, and that's it really. So there's n times sigma squared plus mu squared. Okay? Now you can tell that this expression is starting to simplify fairly quickly. Okay? So we have n sigma squared minus sigma squared, okay, plus n times mu squared minus n mu squared. So the mu squareds cancel out altogether, okay. So we end up with n minus 1 times sigma squared, okay. And then we bring back in our fraction. I sort of disregarded the fraction the whole way through. So we have the whole expression is 1 over n minus 1 times n minus 1 sigma squared. And there we go, sigma squared. So the fraction cancels out with n minus 1. Okay, so that's it.